Hello, my name is Adrian Florea, and I'm an MSRP intern working in Giovanni Traverso's lab in the Mechanical Engineering Department. These past 2 months, I have worked on investigating a delivery method for long-term gastrointestinal wireless electroceuticals. Obesity affects millions of people each year and increases a person's risk for diseases such as diabetes, heart disease, and some kinds of cancer. Though there are many surgical and non-surgical options and therapies that exist for obesity, gastric electrical stimulation, or GES, has been shown to be effective since it targets hormonal and neurological pathways that control food consumption with an electrical pulse. As you can see in the bottom images, current devices for stimulating the stomach walls are invasive and are limited to one orientation once implanted. This limits the scope of patient-specific and non-invasive GES therapy. These two issues of GES can be addressed with long-term ingestible devices. And the first concern for an ingestible GES system is power generation. A review of other ingestible devices concluded that mechanical harvesting methods, including piezoelectric and turboelectric approaches, as well as chemical fuel harvesting, are not sufficient for power requirements for gastric simulators. Electromagnetic power transfer has a much larger power capacity, and it's the method that we choose for our ingestible system. The process for our proposed ingestible GES therapy utilizes a flexible copper antenna for electromagnetic charging. This antenna is a few microns thick, which raises the need for deploying and anchoring the device to the side of the stomach wall carefully, such that the antenna is not damaged. Since the antenna is not suitable to be deployed on its own, this project aims to investigate methods that deploy the antenna from an ingestible capsule and control the location for which it anchors down into the stomach. We also decided to implement magnetic actuation for our device, which would utilize an external magnetic field to be applied to control the location of the device. It's also important to mention that some limitations of this approach are the short working distance of the power generator, as well as the large surface area that would be difficult to manipulate within the stomach. Our first step in investigating delivery methods identified 4 materials as possible solutions. We also identified goals for the device that focus on minimizing weight as well as the antenna deployment reliability. Using material properties such as density and the Young's modulus that address these goals, as well as preliminary prototyping with an antenna substitute, we realized that origami and nitinol-based methods would be too destructive for the antenna, and as shown in the bottom images, would crease or tear the antenna. The orientation and position of the device are controlled by a large external magnet. We studied how the mass of the device would affect the ability to be controlled, especially when it's separated by the stomach wall and other tissues. By characterizing the ability that the device can be controlled in a dry or wet environment and at multiple directions, we can understand the clinical limitations of the device and engineer a material that enables increased usability throughout the stomach. After evaluating the data and results from the previous 2 steps, shape memory polymers were picked as an ideal antenna delivery method. This GES architecture using SMPs was developed after examining various adhesives and polymers. A process for manufacturing these has been outlined for future reference. This video of an SMP is seen unfolding from a gelatin capsule under influence of an external magnet. Overall, it took under 2 minutes for the device to completely deploy in the 40 degrees Celsius water. An in vivo validation of the deployment of the antenna in a swine model showed success in 2 prototypes and deployed in under 5 minutes. An external magnet with a half a Tesla strength controlled the device from a distance of at least 10 centimeters from the stomach wall. The endoscope video illustrates the ability that this device can be controlled within the stomach via an external magnetic source against the force of gravity. Overall, this summer I identified a specific approach to delivering the wireless charging antenna, as well as validated prototypes in benchtop and in vivo settings. In the future, we hope to continue validating the device by testing the electromagnetic charging capabilities in the presence of the permanent magnet and on our prototype. I'd like to thank Gio and Kiwang for this opportunity and for being amazing mentors throughout the summer, also to the Fab and In Vivo team for their guidance and assistance throughout this project. Lastly, I'd like to thank Dr. Noel Wakefield and Maria Cervantes for all their support throughout the MSRP program. If anyone has any questions, feel free to reach out for me. Thank you.